This is probably only going to take me 2 days to teach you. Those 2 days being today and then on Friday. But I'm gonna guarantee you a work day on the Tuesday. Okay, because again we don't have school next Monday. I'm gonna give you a work day on that Tuesday over section 4.3. I believe I could get all the notes done, but even if I don't, it's going to be like 1 or 2 slides, whatever. But I'll give you a work day over section 4.3 on Tuesday, and that means that we will review on Wednesday, review on Thursday, and then we will actually have a quiz over 4.1 to 4.3 next Friday. Quiz over 4.1 to 4.3 next Friday. Okay. So, we talked about how derivatives tell you what the slope are, right? I said a lot in the first semester that don't lose sight of the end goal. The derivative is the slope. Slope is derivative, derivative is slope. Those are the same things. Those are always going to be the same, should be equivalent in our head. So what does that imply about the graph? What does that tell us about the graph? And then we can extend upon that, okay, what does the second derivative tell us about the graph as well? And that's what really section 4.3 is all about. How do we start thinking about what does the graph look like based on the derivative? To see how derivative of f can tell us where a function is increasing or decreasing, let's take a look at that first figure over here. Now, remember that if I think about the slope, if I think about the derivative of the function, that's telling me what the slope is. Like, for example, if I take little snapshots, I need a pen. If I take little snapshots of the slope, okay, going up the hill on my original function, all three of those blue little lines in there have a positive slope, don't they? As soon as I start to go down the hill, as soon as I start to decrease on the original function, those little snapshots of slopes start to turn negative, don't they? The slope of the original function, okay, or I'm sorry, the slope of the tangent line is really dictating whether the function was increasing or decreasing. There's this connection that we have to make about the derivative, if it's positive or negative, the sign of the derivative, and the direction of the original. And when I say direction, I mean, is it increasing or is it decreasing? If the derivative is positive, then the original function is increasing. If the derivative is negative, then the original function is decreasing. What we saw earlier on in sections 4.1 and 4.2 was that if the derivative was 0, it was maxing out or minimizing, right? It was hitting that high point or low point. We not only can tell when it's going to hit a high point or a low point, but we can also tell when the original function is increasing or decreasing. And that's going to give us what's called the increase-decrease test. Okay, I'll abbreviate this to the ID test. So if you're ever looking at a key or anything and you see use ID test, that's what I'm talking about here. Okay, if f prime of x, is greater than 0, I mean if the derivative comes out positive, in other words, if the derivative comes out positive, then the original is increasing on that interval. If f prime comes out negative, if f prime comes out less than 0 on that interval, then the original function f is decreasing. Okay? Because again, the derivative is the slope. Slope is derivative, derivative is slope. So therefore, I can tell what the derivative, based on the sign of the derivative, I can tell what the original function is doing at any given moment. So let's use that. Find where this function is increasing and decreasing. Find where this function is increasing and decreasing. We are going to be working toward being able to graph functions like these without needing calculators, without needing technology to graph them. We're going to be able to visualize what's going to happen on this graph without needing any sort of calculator. Okay, now let's use the increase-decrease test to tell me where this is increasing and decreasing. To do so, I need to find my critical values. And to find my critical values, I just find the derivative. And really, that derivative is going to tell me where the function is going to be increasing and where it's going to be decreasing as well. Okay, well, my derivative is quite easy here. We got 12x to the third minus 12x squared minus 24x, right? So at this point, I can find my critical points pretty easily, right? I factor out an x. Actually, let's factor out a 12x, shall we? Okay, we get a 0 on the left side. We're going to get a 12x, and that's going to be an x squared minus x minus 2. Okay, so that is a 12x, x minus 2x plus 1. Because I know my critical points are the possibilities where these things change, right? I know the critical points are where it changes, it has the possibility of changing from increasing to decreasing. It's the places where it could possibly have a maxing out or bottoming out point. So I know these critical values are x equals 0, x equals 2, and x equals -1. Now, to figure out what's going to happen in between there, I need to kind of put this on a number line and test some points in between. Okay, this is what the increase-decrease test actually looks like. You find your critical values, and then you put those critical values on a number line. So going from smallest to biggest, it looks like it should go -1, and then 0, and then 2. These are the places where it has the possibility of changing from increase to decrease. So now what we're going to do is pick some points in between. We're going to pick a point here, pick a point here, here, and here. And I'm just picking some test points. Pick me something less than -1. Okay, -2. Pick me something in between -1 and 0. Okay, -0.5. Pick me something in between 0 and 2. 1. Pick me something bigger than 2. Okay, 3. It doesn't matter what we pick in between there because everything in between -1 and 0 is going to stay what it is, right? Essentially, -0.5 and -0.25 are going to tell me the exact same thing. If I pick 1 or 1.5 or 1.75, it's going to tell me the exact same thing because if one of them shows increasing, they'll all show increasing. If one of them shows decreasing, they'll all show decreasing. Is what anything that I pick between 0 and 2. So let's see what happens at -2. Let's see whether this function is increasing or decreasing at -2. And to do so, that's going to go back into not the original, but the derivative. Whoa, didn't mean to choose that pen. I'm going to go back into the derivative. Be very careful about what you're plugging it back into. Okay? Earlier on, when we were talking about what were absolute maximums and minimums, we were going back into the original. But I don't really care where -2 shows up on the original graph. I care what the slope is at -2. And to figure out what the slope is at -2, I run it back through my derivative. Okay, so let's do so. We got 12 times -2 to the third power minus 12 times -2 squared minus 24 times -2. Just going to double check I'm putting it correctly. 12 times -2 cubed minus 12 times -2 squared minus 24 times -2. Woo. -96. -96. I care nothing about the fact that it's 96. The value, I don't care. What I care about is the sign. Okay? This came out to be -96. So negative. That's what I care about. I don't care about the fact that it's 96. I care about the fact that it's negative. Because what is that telling me? That's telling me that the slope of the tangent line to the left of -1 is negative, which means my function is going to be decreasing everywhere to the left of -1. So it's going to be decreasing until it hits -1. Let's see what's happening in between -1 and 0. To do so, I'm going to plug in -0.5. I'm going to just repeat this process here, but instead of -2, I'm going to say negative point insert a 5. And we got cubed minus 12 times negative. Oops, 125. Point insert a 5, -0.5 squared. And then we have negative minus 24 times -2. No, 24 times -0.5. 7.5. Again, I do not care about the fact that this is 7.5. I care about the fact that this is positive. Positive. I don't even need those numbers. When you show me work on quizzes and tests, I don't need those numbers. I need you to tell me whether it's positive or negative. I'm showing you what those numbers are for just to begin here. I'll never write those numbers again. Usually I'll just put a positive or negative sign. Let's go between 0 and 2. Let's plug in 1, right? Oh, well, if I plug in 1, that's going to give me 12 times 1 minus 12. So that's going to zero out. Minus 24. Oh, hey, Mrs. Hawk, how's it going? Good. Oh, it's going. You come in and learn some calculus. Take a seat. Pull up a chair. We're doing a little increase-decrease test. So negative 24. That reminds me, I should give out some of this.
She was reading a book that was not related to English.
How about that?
Who knew that could be fun?
It's not. I'm just saying.
Stop math? Now, when you start grabbing my letters from English into math, I get mad.
We make up our own letters.
Yeah, what is this like?
We use French letters. We use...
Gross.
I know.
That's disgusting.
So it's negative 24, right? Negative. Now, let's plug in 3 and see what happens. Okay, let's plug in 3. We got 12 times 3 cubed minus 12 times 3 squared, which is 9, minus 24 times 3. We get positive 144. Okay, again, I really don't care about the value. I care about the sign. Those positives and negatives tell me the direction of the slope on all those little tangent lines. It's giving me snapshots of what's going on. So that means, all said and done, that this function is increasing wherever the derivative came out positive. So from negative 1 to 0, this function is increasing. From 2 onward, this function was increasing. It's decreasing wherever the derivative came out negative. Okay? To the left of negative 1. Negative infinity to negative 1. To in between 0 and 2. You see that? Again, plugging it into the derivative tells us the direction of the original function, whether the original function was going to be increasing or decreasing. Again, tie together the sign of the derivative and whether the original was increasing or decreasing. Those are telling you the exact same thing. The sign of the derivative, whether it's positive or negative, and whether the original function was increasing or decreasing. Now, here's what's really cool about this, and this is the next step beyond this. Okay, if this function, I had said earlier on in sections 4.1 and 4.2 that we knew that negative 1 had the possibility of being a minimum or maximum value, right? Did we know whether it was going to be a minimum or maximum? No. Did we even know that it was going to be a minimum or maximum? No. We just knew that it had the possibility of being a minimum or maximum. Based on this test, I get more conclusive results. Okay, if this function is decreasing all the way until negative 1, and then it starts to increase, what does that tell you about what's happening at negative 1? It was decreasing until it hit negative 1, and then the function starts to increase. Oh, that means that definitively negative 1 was a minimum value. Has to be a minimum value, right? Because it is decreasing, then it starts to increase. And it changes at negative 1. What does that tell you about 0? Well, the function was increasing, and then it started to decrease. So it was increase, and then it hit 0, and then it started to decrease again. So that means 0 is a local maximum value. Then it started to decrease again, and then it went back up after it hit 2. So that means 2 went from decrease to increase. 2 was a local minimum value. I can use the increase-decrease test to tell me what's happening in terms of minimums and maximums. When I make that conclusion, the name changes. It changes from increase-decrease test to what we would call the first derivative test. The first derivative test. Okay? The first derivative test. This you will use way more often. The first derivative test. Well, because I guess it's good to know what's going on in terms of the original function increasing or decreasing. What's really important is where the maximums and minimums are. Okay, where the maximums and minimums are. Drawing the conclusion about where a function is minimizing or maximizing or optimizing, that's the really important piece. And that's what we're going to be using it for. It's called the first derivative test. It's essentially the exact same thing that we just did, but now making the conclusion based on whether it's increasing or decreasing, where we have maximums and minimums. So here's the summarization of the first derivative test. Suppose that C is a critical number of a continuous function. Notice that we're preserving continuity here, right? It has to be continuous, because if we can't guarantee continuity, then we don't know, just because it was decreasing then increasing, what if there was a discontinuity somewhere in there? Well, then I wouldn't be able to use it. Okay? I wouldn't know for sure whether it was going to be a maximum or minimum. Okay, so our first derivative says that suppose that C is a critical number of a continuous function. If f prime, if the derivative changes from positive to negative, if f prime goes from positive to negative, that means my original function goes from increase to decrease, then there has to be a local maximum at that value. Then there has to be a local maximum value at that C, at that critical point. It goes from positive to negative. If it goes from negative to positive, if it goes from decreasing to increasing, there must be a local minimum. Now, what we hadn't looked at, because the function didn't have it in there, is this third option. If f prime is positive both on the left side and the right side, or negative on both the left side and the right side of a critical value, then it does not have a local maximum or minimum point at that value. Remember where it bent through in x to the third? That's the third option here. Okay, if we run that first derivative test on the basic cubic function, we would see that it increases. Just think about the cubic. It goes up and up, right? It doesn't decrease. It goes increase. We would see positive on either side of the critical point. And if that's the case, then it doesn't have a local maximum or minimum point at that value. Something else is happening. We don't know what it is, but something else is happening. Okay. They say, they use the wording, the first derivative test is a consequence of the ID test. You know, it's kind of like, it's something, you do the ID test within the first derivative test. Okay. You're doing the increase-decrease test within the first derivative test. The only difference in the name is that you're drawing a conclusion about maximums and minimums when you're using the first derivative test. The ID test just tells you where it's going to increase or decrease. Okay. And here are the illustrations of the different possibilities that you could have. You know, if the original function goes from increase to decrease, that means the derivative is positive and then negative. That means there's a local maximum at that point C. If the derivative going from negative to positive, there's my local minimum. Okay, this is A. This is B. That's an illustration of A, and then an illustration of B. This is the illustration of the two parts of C. If it's positive, it flattens out. You get my critical point. It's positive and positive. The derivative is positive then positive. The slopes are positive and positive. There's no critical point, there's no maximum or minimum value in there. It's just a critical point. Something else is happening. It's probably bending through. Probably. I don't want to say definitively, but most of the cases it's bending through. If it's negative, slope is negative, it flattens out, and then it's negative again. Okay, there's another critical point that doesn't have a maximum or minimum value in there. Okay. All right, well, let's do the first derivative test on that thing that we just did. Okay. So look at example 2. It's the exact same function as example 1. Let me just copy. Actually, you know what? I don't need to. Let's run the first derivative test. Okay, we would run the ID test, and then we would say, where are our local maximums? Well, we would say that there are local maximums at, okay, so we got to look at this again. This one, negative, positive, positive, negative, right? Increase to decrease. There's a local maximum. How do I want to put this? I want to put it at, do I want to use a coordinate? Yeah, I think so. Local max at 0, something. I don't know what that something is yet. I know that it's a coordinate. There's a local maximum somewhere. So this is a local maximum at 0 because it goes from positive to negative. But then there are 2 local minimums. One at negative 1, something. The other one at 2, something. Because it's going from negative to positive at negative 1. It's going from negative to positive at positive 2. Now, how do we find out the y values of those coordinates? How do we figure out where that actual high or low point is? Well, we can just run that through the original. Don't run these points through the derivative. What would happen if I run those points through the derivative? It would give me 0, right? Because these are critical points. So don't run them through the derivative. Run them back through the original to tell me how high or low does it go. I know that this is a local maximum point, but how far up does it go? Does it go to 100? Does it just go to 10? Let's see. If I go back to my original, oh, that's my derivative. If I go back to my original, this would be 0, this would be 0, this would be 0. I would get 0, 5, right? So I know my local maximum point is 0, 5. Let's run negative 1 through my original. So 3 times negative 1 to the 4th minus 4 times negative 1 to the 3rd minus 12 times negative 1 squared plus 5. Okay, 0. Oh, really? Negative 1 is 0. Oh, cool. Negative 1, 0. And then we run 2. Let's run 2 into that. So 3 times 2 to the 4th minus 4 times 2 to the 3rd, which is 8, minus 12 times 2 squared, which is 4, plus 5. Negative 27. And now I can start to get a better idea of what this function looks like, right? I know how high or low my maximums and minimums are. I know where it's increasing and where it's decreasing. I know a lot more about the graph based on this first derivative test. Okay, let's do one more first derivative test. I feel like we did this. X plus 2 sine x. I feel like that was in section 4.1 or something like that. But it's not too bad to do. Let's first off start by finding g prime. G prime. Well, that is 1 plus, what's the derivative of sine? Cosine? 1 plus 2 cosine x. And we find the critical points by setting that equal to 0. 1 plus 2 cosine x is equal to 0. So 2 cosine x is negative 1. So cosine of x is equal to negative 1/2. Okay, what locations give me a negative 1/2 as my x value? It's cosine. It's the pi over what family that have the x value of 1/2? Pi over 3 family, right? So if it's a negative, it's up here, right? So that would mean 2 pi over 3. Or down here, it's the 1, 2, 4 pi over 3. Right? Yeah. 4 pi over 3. Yep. So we have 2 pi over 3 and then 4 pi over 3 within one rotation of 2 pi, right? 0 to 2 pi. Okay, now let's run the first derivative test on this. Let's run the first derivative test on this. I really don't care what's happening beyond to the left of 0 or to the right of 2 pi, right? I really only care what's happening here. I really only care what's happening here, here, and here, right? You know what's really easy to find, though? Let's pick 0 and 2 pi. And heck, why not? Let's pick pi in the middle there. Those are probably pretty easy to find. What if I plug in 0 here? What's the sign of 0? What's the y value at 0? Angle 0. It'd be 0 again, right? Over here. The y value at 0 would be 0. So this is 0 plus 0. Oh, wait. Oh, I don't want to use that. Oh, stupid, Mr. Laverick. What was I trying to run it back into? The original. First derivative test. Derp. Go back into this, right? Sorry. Go back into here, not the original. Okay, so 1 plus 2 cosine x. What's the x value here? 1, right? 1 plus 2 is 3. Do I care about whether it's 3 or not? No. I care about the fact that came out positive, right? It came out positive. What about pi? Okay, over here. What's the cosine here? What's the x value here? -1. So this is 1 plus 2 times -1. 1 minus 2 is negative. What about 2 pi? Isn't that going to come out the same as 0? Okay, now I see my signs. I can tell you definitively that there is now, what is 2 pi over 3? Is that a maximum or minimum? Well, it was increasing, then decreasing. Increase, then decrease means maximum point. There is a local max at 2 pi over 3, comma something. And then it goes decrease to increase. Local minimum at 4 pi over 3, comma something. And now to figure out where that occurs, we would just run it back into that goes back into my original. See, I told you it was tricky to figure out where things go, right? That goes back into the original because that's going to tell you how high or low it goes. So just to kind of cheat or beneater here, that 3.83 and 2.46. And all I'm doing there is just plugging 2 pi over 3 back into G. And then 4 pi over 3 back into G. Okay. All right, so we're about this far away through the notes. Okay, about halfway through the notes, I would guess. Cool. So again, tomorrow we got that senior assembly, and then Friday we will finish the notes for section 4.3. Work day Tuesday, and then we will review the rest of the week for the quiz on Friday of next week. This is where it starts to get real fun. I like this